Thank you for coming to my talk, The Things You Left on the Table. I'll explain the title in a moment. But I just wanted to start with a slide that I think should be kind of standard these days with AI assisting everything. I did use AI to help me at least start the writing of this talk. I used it to challenge and expand my ideas. I used it to do research for me, and I used it to upload some of that research data to the slide deck in Slides. So it just sort of sped me up, but in no terms did it write the talk for me. So this is very much my talk that I'm giving you today. So I'm just going to, just as a sort of prelude to actually talking about the topic, I do need some audience participation, but don't worry, I'm not going to point at anybody and ask them to answer complicated questions. So could you just raise your hand if you're really excited about test coverage? It's nice to see some hands. I knew there'd be some fellow fans out there, test coverage. Could you raise your hand if you or your boss is really excited about AI right now? Okay, so that's a few more hands. It's not quite as many as I expected, but maybe people are a bit tentative about the changes that are happening. This is not a talk about AI, but it is a talk driven by AI and the rise of AI agents specifically. I will be kind of tying things together with AI towards the end, but I'm actually going to spend a lot of time not talking about AI, very, very definitely. So first, and I apologize for this, I didn't realize the screens were going to be so big. My name is Mark Smith. I'm commonly known as GD2K online for reasons that aren't that funny. And you can see me wearing a stupid plastic Viking helmet. I work for JetBrains. I have this amazingly grand title of Head of Python Ecosystem, which means that I'm responsible for PyCharm, your favorite editor. Do come and talk to me about that later. It will be making an appearance in this talk, but this is not a talk about PyCharm. I've also, in the past, I've been a chair of DjangoCon Europe. I'm an organizer of PyCon UK. I run Python Edinburgh, my local Python meetup, quite badly. And just generally, I'm very excited to be here. I've been wanting to come to Lithuania for a long time and never quite managed to make it. I've always wanted to come, and when I did some research for this talk, I discovered, I wanted to know if Vikings had ever invaded Lithuania, and I discovered there was a little bit of that, but actually more importantly, the Lithuanians in the 12th and 13th century were known as the Vikings of the land. So I thought, I'm going to fit in quite well here. But I'd like to tell you a story about a minor obsession of mine, because I always think with keynotes, they benefit from being a little bit personal, so I hope that's okay. So I want to talk about something that I keep on my desk at home. A desk is a type of table. This actually isn't the keyboard that I have on my desk right now. This was the first keyboard I think I ever bought rather than kind of having assigned to me in an office. I bought it in 1999. It's a Microsoft Natural keyboard. You're actually going to hear the name Microsoft or see the name Microsoft quite a lot in this talk. It's not intentional, just a coincidence. And at the time I bought this, I couldn't type properly. I kind of hunt and peck typed with 3 fingers. And I wasn't very slow. I could get the job done. I used to type at about 30 words a minute when I tested it, but it wasn't very efficient. But I bought this keyboard, and as you can see, it's split in the middle and it's a little bit raised, so your hands kind of sit either side of it, which is quite nice, very comfortable. But it started to feel weird hunt and peck typing on this sort of like this lump. So I decided to teach myself to touch type properly, like a real typist. That's where you keep your fingers on the home row and you only move them to hit specific keys, and you move them back to the home row. It allows you to type without looking at the keyboard at all. And so my typing dropped to 5 words per minute. But gradually I managed to speed up a bit, and I got to maybe 45, maybe 60 words per minute in short bursts. But I got benefits that I hadn't been expecting. One was that there was this pain that I used to get in the middle of my back that just went away. So obviously it turns out that kind of moving my hands around a bit all day was causing quite a bit of stress in the middle of my back. This was in my early 20s, so I think I've actually really avoided some problems in the time since then by literally just teaching myself to type properly. And I could finish typing a sentence while looking over my shoulder if somebody was trying to get my attention. That was kind of cool. People used to get quite freaked out about that. But the side effect that I really wasn't expecting, and I think has been longest lasting, has been that I could think more while I was typing. So this really wasn't something I was expecting. It was like a part of my brain had been cleared. So I was no longer kind of flicking my eyes up and down between the monitor and the keyboard, which even if you don't know you're doing it, you are doing it if you're a Hunt and Peck typist. But it seemed like that cleared part of my brain, and I could concentrate more on the thoughts that I was having while I was putting the words into the computer. This was such a success, I decided to do something else slightly stupid. So I taught myself again to touch type on a completely different keyboard layout. This is a Dvorak layout. I know I'm not pronouncing that right, but he was an American, so I think that's probably how he pronounced his own name. This was designed by Dr. August Dvorak in 1936. One of the interesting features about this keyboard, it was designed to make you more efficient, is that you can type 50% of the words in the English language without moving any of your fingers away from the home row. So it has all the vowels on the left-hand side, and it has the most common consonants on the right-hand side, all on the home row. Wikipedia says, despite studies showing that it could improve speed by 74% and reduce hand strain compared to QWERTY, it failed to displace QWERTY due to the retraining requirements. And now I could type up to 90 words a minute in short bursts, which was pretty cool. At this point, I really went off the reservation and I bought myself an Author Linear keyboard. You'll notice the keys aren't staggered on this. It looks amazing, just like a sort of chocolate, a bar of chocolate. I absolutely love this thing, but it is terrible to type on because the keys are so close together. You either have to angle your hands to put them in the right place, or you have to move your elbows in like this, both of which are terrible for your posture. So that didn't last long. And so I spent a bit more money and I bought a Moonlander. This isn't quite Author Linear. It's like the key layout is slightly curved, so they naturally sit under your fingers with the shape of your hand. But, and this is very important, and this is where I tie it back into the topic of the talk, none of this seemed to make me a faster programmer. I thought being able to type faster would make me a more efficient programmer, but it didn't seem to make much of a difference at all. I started to realize that actually I didn't spend very much time typing at all. I spent a lot of time thinking and a lot of time doing other things. The actual typing of the code was a minority of the thing that I was doing. So I got really into coding challenges at one point. This is a site called Code Wars. It allows you to solve programming problems. It starts with really simple, practically print line problems that are described down the left-hand side. And there's some hidden unit tests that it runs against your code each time you submit it. And then when you get all the tests to pass, you have passed the exercise, and it gives you a more complicated exercise to do. And you get points, and everybody loves points. And you get to compete against your friends, which is also a lot of fun. So I spent quite a lot of time on that. But this also didn't make me much of a faster or more efficient programmer, because I don't actually spend that much time solving these sort of algorithmic problems that crop up in these coding tests. You know, it's helpful if one of those things do crop up, but to use an example from one of the lightning talks, we don't spend a lot of time reversing linked lists day to day, which is kind of why we get annoyed when we get presented that as a coding test in an interview. It's not an example of what we do in our jobs. If it was something that we did commonly, it would be part of the standard library or part of a library we could download, and you would just do it. You could just call a function and pass it your linked list. But it was fun. Do recommend this kind of thing, but it had absolutely no effect on my day-to-day job. A few years later, I bought a book called Rapid Development. I didn't buy it because I wanted to read it. I bought it because I thought it would make me look good at work. I had a CEO in the medical startup I was working for who thought he could code. He had done some coding as part of his PhD, had never worked as part of a team, had never written a test, had never put any code into production, and he was always frustrated by how slow the developers in the company were. He felt that we took a lot longer than we should do to solve the problems that we were solving, which was all around medical imaging. And he thought that if we would just let him at the code base, he could fix all of our problems overnight. But it was a medical software company. Very important that the code actually worked, so we didn't give him access to the code. But I thought if I had this book on my desk, like maybe it would impress him when he walked past. Needless to say, he never walked past my desk and never noticed that I had this book on my desk. But one day, one of the senior developers, a guy I really respected, came past, pointed at the book, and said it was really good. He had read it. And he summed it up in a way that really I can remember 20 years later, which is he said, the theory of the book is that to speed up your development is actually to follow best engineering practices. That's the best way to speed up a development project. And that was a bit of a revelation to me, because I've been working in various startups, and we always thought there were kind of two ways to develop code, to develop our products. One was sort of fast and bad. It's that you don't worry too much about testing, you just throw out the code and you'll fix the bugs later. That's kind of the compromise that you're making. Or there's slow and sure, which you can never afford to do because you need to get the features out as quickly as possible. And so for there to be a book out there that would tell me that actually the best way to develop software faster over the longer term was to develop it the right way was quite a revelation. I did read the book in the end, and I would sum it up slightly differently to that software engineer back then. I would sum it up as rapid development may include following best practices, but primarily to speed up your development, you should focus on the things that make you fast. So that means you bring it into the way, the process of developing software is you think about the things that are slowing you down and you try to solve those, and you think about the things that make you more efficient and you solve those. And that may well be best practice. For shorter term projects, for smaller projects, that may not be the same thing. So this is a talk about the things that make you fast, that you may or may not be doing, or you may or may not be investing enough time in. Anyway, let's debug some code. So here's some code. There's a bug in it. The bug may be reasonably obvious if you're just scanning it and looking for idiomatic Python code. It's a toy problem. But we know this isn't working. There's a comment at the bottom that says it's returning the wrong value. It's printing 44.97 instead of the expected value of 59.94. So I'm going to do what I always do. I'm going to stick some print statements in, and then I'm going to see what the results are. So let's just check that it's getting the right input. You could watch me type this at my amazing 90 words a minute typing speed, or I've got a shortcut that will just do it properly without any mistakes, hopefully. So yeah, I'm just printing out the items that are going in and printing out the result just to sort of check that the inputs and outputs are okay. So let's run that. This is PyCharm, by the way, isn't it lovely? So we've got the items, and that's this list of dictionaries. Really, those should be classes. This is terrible code. It needs some refactoring. And then there's a total, which, as I said, is 44.97 inside the function. So that's great. I mean, it's confirmed what we knew, but it's not really telling us anything. So I'm going to have to get an insight into what's happening inside this loop. So I'm just going to stick a line in here that prints out like everything. We've got to the point now where I just need to know everything. So now we're going to print out I, which is the index of the current item being looked at. I'm going to print out the name of that item to make sure we're looking at the one we think we are. And I'm going to print out the running total rounded to two floating places. So let's just run that again. Okay. So we've still got, I forgot to remove the previous print statements. That's a common problem, isn't it? And then we've got the items again, and then it starts going through them, and it only prints out the first two. So we've got 0 and 1, and then it's obviously not getting to the last item because we have an off by 1 error here, because range is exclusive of the value that you put in. Now, a real Python programmer, or a more experienced Python programmer, wouldn't write this line, but I needed something that didn't work. So this is what you get. So I'm going to delete all my print statements, probably miss one. Oh, there we go. And then I'm going to do that again. So this isn't working. I need to know why. So I'm going to stick a breakpoint in here, and then I'm going to hit the debug button. And now it's stopped, and I have the whole state of the function at this point in time just before it returns a value. I promise this whole talk is not just going to be an advert for PyCharm. You can do this in VS Code. You can do this with PDB. So like none of this is really a PyCharm advert. But I is 1. So we can immediately see we didn't get to the end of that loop because the index of the last item is 2. If I needed to see inside the items that were passed in, I could have a look here. I can see the totals wrong. So I have all the information at hand to solve the problem in a single place, rather than having to repeatedly work out what I might want to look at and run the program again. So I think even without me typing those print statements out in front of you, you can see this is a bit more efficient, even if it is a toy example. So let's just move back to my slide deck. I have to remember exactly the right key combination. So yeah. So this is the way I would write that if I was actually writing idiomatic Python, just to prove that I am a Python programmer. I would have a generator expression and pass it to sum. That's nice and easy. I love the fact that Python intrinsically just avoids these off by one errors that are actually really common in other languages. And if I was really going for bonus points, I would stick in the type signature of my parameter and the return type. And that gives me two advantages. So it allows me to run something like MyPy or Pyrefly or TY against my code. And if there's any code in my code base that's passing sort of an invalid type, the wrong type into that, it will catch it before I even have to write a test. So that's kind of a form of testing, is defining your contracts. And on top of that, any decent IDE will now have more chance of telling me what variable I might want to pass in, or what I might want to do with the resulting values, because it understands a bit more about my program than it did before. So I get auto-completion, which will make me faster as a developer, or at least save me some typing. So the debugger is right there. You can set breakpoints and stop at any part of your running program. You can step through the code line by line. You can step into functions and out of functions. You can set watch expressions, which effectively are print statements, but they're a bit more powerful. You can have conditional breakpoints where it will only stop when a certain state is reached. That can be kind of cool for just making sure you're not repeatedly hitting a breakpoint that you're not interested in. These aren't advanced features. They're the basic features that people never get around to learning. And yet, only 23% of debugging sessions use a debugger. So the majority of debugging sessions are doing the slow, inefficient former thing rather than the efficient, slower thing. I may have got those words around, excuse me. This is backed up by actually some research we've done at JetBrains as well, that states similar numbers. 58% of developers use print or logging as their primary debugging method. And the question really has to be why, especially given that, according to the Stripe, this research that Stripe did, 42% of developer time is spent on maintenance, debugging, and debt. So we actually spend a lot more time solving problems in our code than we think we do. We think we write code for a living, but we don't. We spend our time trying to understand what our programs are doing. There's another study that says that developers actually spend around 50% of their time debugging. I haven't read into the detail of that research, so I don't know whether that's like the amount of time they spend at 50% of the time they spend at a keyboard, but it's certainly a significant proportion of some time. And I apologize if this sounds a bit like an old man yelling at a cloud. I'm not judging you, because I am also a print line debugger. I'm the person who types in the print statements instead of using the debugger, and I work for an IDE company, so it's really unforgivable. I don't even know why. I know how to use the debugger, and I know it's more efficient, so this is just bad habits ingrained. And I spent all that money on keyboards. So debugging in Python, it's just there. If you are using the inbuilt debuggers, you've got Breakpoint as a built-in since 3.7. You've got the debugger that comes out of the box. PDB is perfectly valid for doing debugging. It's a little bit hard to use. If you want a slightly easier console debugger, you've got PDB++, IPDB. I'm sure there are others. I think there was a BPDB at one point. If you're using an IDE, it almost certainly has a debugger in there, almost has at the very least the basics of the features that I showed you. This is not to say that logging is never valid. Actually having logging statements in your application to explain what's going on is useful, because once you put your software into production, it's going to be a lot harder to stop it in the middle and then start setting breakpoints and things. So you're almost certainly going to want to do post-mortem debugging, where you just get the logs through some sort of application monitoring system or something like Sentry that's providing you with the information you need to work out what did go wrong at some point so that you can fix it in development. So solving bugs faster is only half the story. The other half is when you find them. So I want to talk about testing and shifting. Let's talk about the cost curve. This may be something you've come across before. It's not rare knowledge, and it gets quoted quite a lot. But the idea is this: like if you introduce a bug into your application, if you find it and fix it while you're still developing the code, it will take a certain amount of time to fix. That might be 10 minutes, it might be an hour. That's represented by this orange dot in the middle of the screen. The problem is if you don't fix it in development and it makes it through to staging and it gets fixed by somebody in QA, it takes a bit longer. It takes 10 times as long to fix. So you think about the cost here. At the very basic, there's two people involved, right? There's a developer and a QA engineer of some kind, somebody testing the application. They've then got to find out how to reproduce the bug. They then have to write that up in a ticket. That then gets back to the developer. That then has to be scheduled. The developer has to pick it up. They have to create a new branch to reproduce the problem. They then have to reproduce the problem. They might not succeed. They might have to go and have a chat with the QA engineer. You get the idea, right? It's like this is more expensive than it seems. And what's worse than this is if you don't catch it in staging and it makes it through to production, it takes 30 times as long to fix. And this is because you're having to do post-mortem debugging. You haven't got the tools available anymore. It's like trying to debug something through a letterbox with one hand, I guess. And there's various studies and they come up with different numbers, but they're all kind of similar proportions. Some of the studies say that it's actually 100 times more expensive to have a bug in production. So the more that you can shift bug detection to the left, the more that work is worth, right? It's like you can spend 10 times the amount of time over on the left, and if it catches all the bugs that we would otherwise catch in QA, it's actually going to be worth it. I don't recommend you spend 10 times as long on this. With test-driven development, there's a stat here from IBM and Microsoft that says that 40 to 90%, there are 40 to 90% fewer defects with 15 to 35% more development time. So actually, there's some really solid statistics that back up a bit more time spent in testing has these effects. So yeah, this is just sort of talking about what happens when you shift it to the left. You get a 30 to 100 times benefit if you could move it from production into development, 10 times if you move it from QA into development, and 3 to 10 times benefit if you could just catch it in staging rather than production. So that's still pretty significant. You've almost certainly seen a version of this slide before. There's different terminology and sometimes there's some more sections in there. But the idea here is that there's different types of tests and you should have different numbers of each type. You should have more unit tests, which are small and fast to run and reliable. And you should have fewer of these end-to-end tests. There's a common problem that people write too many end-to-end tests because once you've kind of written one, once you've got that infrastructure in place to spin up your application with a dummy database of some kind underneath it, it's relatively easy to kind of prod it to check its behavior. But if you actually find a bug, it's useful for just sort of making sure that everything's sensible, everything's running together. But if you find a bug, you've actually got this whole path through your application to try and find things. So it's easier to debug things if you can find them in unit tests because it's testing a much more sort of a smaller piece of code. I would say, I think in Python, dynamic languages like Python, I think integration, there should be a fat pyramid. I think we should have a few more integration tests. It's perfectly possible to change the function, a signature of a function, and then your test will fail. So you fix the test for that function because to adapt to the new signature, and then your tests are passing. But if you haven't changed all the code that calls that function, then your application is broken, even though your tests all pass. And this is just because we don't have a compiler, right? This is something that in another language would be caught, that you can't call a function with the wrong values in something like Rust. But the biggest benefit to shifting left was to catch production bugs. So it's good that we're catching more bugs by having a decent testing infrastructure, but we want to catch production bugs during development, which is a very different environment. And how might we do that? It's another best practice, right? It's design and refactoring. So good tests allow you to refactor more confidently, deploy confidently, onboard new developers because they act as documentation and guardrails for people working on that code. But good design is the thing that keeps things from breaking in the first place. And the reason this is important is because of these numbers. So developers waste around 23% of their time on technical debt, according to one study. Organizations with high debt deliver features up to 50% slower. So this is another multiplier, right? This is another 2 times multiplier if you can reduce technical debt. 94% of large projects end in partial or total failure, which is a pretty appalling number. I don't know how long that 94% takes. I've worked on some of these projects where it was nearly impossible to make a change because everything was just a big ball of mud. And so it's difficult to know where to put the code, and wherever you put the code has all these interactions throughout the code base that then need to be fixed. So it's like every new feature is really an act of debugging rather than an act of development. And to talk, like the basic thing that a good design gives you is a place to put your code. So that speeds things up, right? You don't have to think so much. Like thinking takes time. So having good design means at the very least there's an obvious place for new features. There's classes that can be extended or implemented. A bad design means that every feature is a negotiation. So this diagram is from Architecture Patterns in Python by Harry Percival and Bob Gregory. And it may look overly complicated to you, because as Python developers, we tend to take very direct solutions to problems. There's maybe been a bit of a resistance to what other communities would kind of call architecture. And the reason this may look complicated is because it's not really solving a problem, right? Not a direct problem. It doesn't handle a request anywhere here. That's another part of the application. Instead, we've written a domain model. A domain model is really a set of objects that belong to a business. They're not a database model. Very much not a database model. They are things that the business does and the things the business does with those things, if that makes any sense. It's like assigning orders to an inventory, that kind of thing. And then on the right-hand side, we've got an abstract repository, which is very much like of the Java world, having abstract objects and factories and things. And this is more of a principle than a class necessarily. You might not actually implement this, but it could be a protocol, for example, given that we have duck typing. But here there's an abstract repository that defines the things you might want to do to the database now. How do I want to store my data? How do I want to access my data? And then the actual implementation written using SQL Alchemy is then the thing that actually talks to the database. But just the basic principles here, there's separation of the different concerns. That means you kind of know where to put code, providing it's part of this problem that's being solved. And if this was a very small code base, you don't need that. If it's just a single file, you definitely don't need to implement domain-driven design. But if you've got a larger code base, it becomes more and more important because it becomes harder to find the right place to put your code. But I actually left one of the major benefits, I left off this diagram, which is tests. So being a book by Harry Percival, who's written a book about testing, the tests are included as part of this. These things are more testable, partly because they are kind of abstract. So as well as having an implementation of the SQL Alchemy repository, we can have an in-memory repository. We can run the same tests against it as we would run against the SQL Alchemy repository to make sure it behaves the correct way. And then we can use that for all of our testing. Anything that interacts with a repository, we give it a real repository. And anybody who's worked like really heavily with mocks will know that like, they're a bit of a foot gun waiting to happen. Like the number of false positive problems that I've had with mocks over the years is quite something. But once you've got your design in place, you need to maintain it. So design decays over time if you're not constantly managing it. And the solution to this is really continuous refactoring. And I know we've all heard of refactoring. Refactoring's been a part of PyCharm since the beginning. It was the main reason people got excited about it. It was these ability to hoist variables and rename things through code bases, these sort of small, discrete code maintenance tasks that we automated. But refactoring is not something you're meant to do in an ad hoc way necessarily, and it's not something that you create in a bug ticket that then goes in your backlog to get fixed at some point. Must refactor X module. It's part of the development cycle. So you write some code, you write some tests, not necessarily in that order, and then you run your tests, and when they pass, you then have another look through the code and you go, how can the structure of this be improved? How can I make this more readable, more understandable? How can I make it more robust, so harder to mess up? Like maybe put some type signatures in. And this is all how you avoid what we generally these days call tech debt. So I do want to have a little rant about tech debt while I'm on the topic. So tech debt is a loan. You take it out consciously. Tech debt is what you take out against your code base when you just need to get this feature in for tomorrow's release. And you know it's going to bite you. You know there's going to be bugs in it. And you know it's not maintainable, but you're going to fix it soon. The ticket that comes in is actually like fix the tech debt. As soon as you write that code, there's a ticket that goes in that gets prioritized to remove the tech debt. If you're just working with an architecture that's bad to work with, that's not tech debt because you didn't consciously take it out. That's just bad engineering. See, I said it was a rant. The general thing about design generally is that when requirements change, it will adapt to those requirements. So you might need to move about some of the code. You might need to create a new abstraction of some kind, but you're not going to have to make changes throughout your code base. Or you're not going to have to refactor. It's not even the word refactor. It's like redesign your entire application. So those are the main topics that I wanted to cover, but I just wanted to do a few kind of quick fire things that also, they're best practice. You've heard of all of them, but I have some stats that I wanted to show you as well. So the first thing is continuous integration, continuous delivery. I really should have written those out in full. I've got plenty of space on this slide. So these are kind of, I think most people would consider these to be standard, especially with things like GitHub Actions. And I know there's been some stability problems about that recently. But like continuous integration is a relatively easy thing to implement these days. There's a few platforms designed for it. And that's just running your tests every time you push code, every time you share code before it ends up in staging or production. And that seems like a sensible thing to do. Run your tests, ideally in an environment that's a bit closer to production than your development machine. You're going to catch more tests earlier on. And that's that whole point of shifting things left, making yourself more efficient as a team. And also delivery is something that you're going to have to do regularly anyway. So why not automate it? Right? It's like if you're having to do it manually each time, that makes it error prone, that makes it slower. That means that somebody has to be dedicated to it rather than it just being something that happens behind the scenes. I know delivery is hard. It involves perhaps database migrations, especially in the enterprise when you're running lots of servers. It involves like blue-green deployment where you've got a whole bunch of servers running version 1 and then you put version 2 on one machine and you check that there aren't any bugs and it's still being performant, and then you put it on a second machine and just check that's still okay, and then you roll it out across all of your machines, and now you're ready to deploy version 3 once version 2 has been deployed, and then you roll back obviously if anything goes wrong. It's not the easiest thing in the world, but you're going to have to do that anyway, right? It's like if this is a manual process or a semi-manual process, just remove that manual part of the process. And yet, despite this just making sense because it's a repeated task that doesn't require like a huge amount of intelligence, so only 45% of teams automate release into production. So this is another place where about half of teams can actually really get some benefits. And then there's code reading. So the reason this reads weirdly as a sentence, code reading detects 80% more defects per hour than testing alone, is because this was written in the mid-90s when code review wasn't a practice that anybody did. And so, yeah, it's weird wording. It comes from Code Complete, which is just, I wish there was a third version of this book, but it's such a good book about the practice of development. Just a bit dated these days. Code reviews have to be careful and consistent, like considered, sorry. They can't just be rubber stamping, can't just be the looks good to me kind of code review. That requires some discipline on the person creating the pull request. It's like you can't just submit reams and reams of code. You might want to divide your pull request into nicely ordered commits, so you're telling a story of the thing that you've developed piece by piece. Quick turnaround is important. Like you need to do this within a short space of time. Otherwise, you've just got developers waiting. And if developers are waiting, even if they're working on something else, those context shifts to kind of come back to code that you've like mentally pushed off is like going to slow you down. And this is a talk about developer productivity. So it's like you have to keep things moving. Every hour on code review, and I have another slide for this, I forgot. Oops. Every hour on code review saves up to 33 hours of maintenance, according to a survey by Codus, who I've never heard of before, but they have a whole blog post that I have in my notes about this. So it's not insignificant, like the benefits. Like you should actually spend time on code review because it's another big multiplier later on in terms of quality and delivery. And then finally, a thing that engineers, I think, don't often think about in terms of making a development team more productive is you have to build the right thing. So this comes back to product management, which is not something I've spent a huge amount of time thinking about in the past, but now I am a product manager, and so it becomes quite important. It becomes sort of a never-ending set of conversations that I have. So if you build something that nobody wants, you've just wasted all of that development time and the testing time and all the rest. And if you think about how long it takes to develop a feature, that can be a week, it could be a month, it could be a year to develop a complex feature. And if at no point during that time do you confirm that that's actually something your users want, then you could be investing all of that development time in the wrong thing instead of the right thing, which is hugely costly. This 64% features stat in the middle is for internal products. So if you've got fewer users, and so if you don't have, if the feature is used rarely, it may not be worth developing at all. Now that I manage a product that has millions of users, like we can have 5% of our users really like a new feature, and that's still valid, perhaps in some cases. So we have slightly different conversations about whether features are needed by a wide user base or not. But generally, the way you solve this problem is you talk to users early, before you've written a line of code, perhaps. You ship small, potentially you vibe code something, whether you vibe code it into your app or you vibe code it as a separate sort of proof of concept thing. AI has some benefits here, and you get feedback and you incorporate that into your product cycle to make sure that you're building something that people actually want to use. So that's sort of the end of the productivity section, and I'm going to be a little bit facetious with this slide. So I'm going to talk about becoming a 10 times team, so a team that's just many multiples more productive. So we'll do some maths. I was trying to work out how much typing faster, how that would make you more efficient. I think maybe 10% more efficient. I might be being optimistic there. But honestly, it's just going to blend into the numbers. User debugger. So if we do spend about 40% of our time debugging and we get more efficient at debugging, whether that's using like a debugger or other processes, maybe a 30% improvement to the time we spend developing. Build the right thing. I couldn't think of a number here. So I've just said double. If we halve the amount of pointless features, that means we're doubling the number of features that people actually want. Fix bugs in development. Whew. So that's 10 to 100 times improvement in productivity, because that's going to maybe 5 to 50%, given that there's a sort of an inverse multiplier on this one. You do that through test coverage, code review, continuous integration, trying to catch bugs as soon as possible. Keep your tech debt low. So there was a stat, I think I mentioned the stat earlier, that high tech debt projects are potentially 50% slower to deliver. And if you work out all of this, you get like your team is going to be 58 times more productive at minimum and up to 582 times more productive. And obviously this is all, as I said, being slightly facetious here, but if these stats are true and they are based on real research, even if productivity is a very difficult thing to measure, like potentially there's some real gains here if you focus on the things with the bigger numbers and spend some more time on those and spend some time thinking about how you could be more efficient at those parts of your process. While we're on the subject of 10x, I do want to talk about 10x developers. I feel like it's a bit of an elephant in the room when you talk about this topic. So you'll find people talking about 10x developers. They are supposedly developers who are 10 times as productive as another capable developer. And there's been some interesting research around this. And generally, although these developers do exist, they are actually 10 times developers compared to low performing developers who are very much outliers in terms of the amount that they produce. So already, like, this is a big drop in terms of their productivity. They tend to specialize in a very specific area. People like John Carmack are often quoted as 10x developers. He's a games developer. He works in a very specific area. They are productive at specific tasks some of the time. So there's a massive variety between the times where they are being 10 times as productive as somebody else doing the same thing, and then most of the work is actually like done at a lower level. And half of the variance of 10x developers is actually day-to-day fluctuation, not like comparison with other developers. And finally, they are rare. So you probably aren't one, and you probably can't hire one. So they're not actually worth spending too much time worrying about, because you're actually just going to be working with capable developers who actually overlap with the abilities of 10 times developers most of the time. So the real multiplier in practices is proven to be the real multiplier for teams is proven to be practices and environment, not individual talent. So it's worth focusing on those things. Hire capable developers and make them productive through the environment that they're working in. There's this, I'm not going to read all these out because there's too many, and I apologize for how much there is on this slide. But there's this great blog post called The Myth of Individual Programmer Productivity by this guy, Bill Nichols, and he just finished it with these whole bunch of really common sense tips for making the average development team much more productive, including things like provide a quiet workplace so that programmers can focus, and teaching quality to developers. Hopefully I'm improving that a little bit in this room right now. Quality can be taught, and it has an effect on productivity. So just teach your developers to write high quality code, and productivity should flow from that. So I said this talk was going to cover AI. So now let's talk about AI. There are lots of conflicting stats about AI and developer productivity. I've looked at quite a few of them. I don't think we know enough to make a decision. Everybody picks a stat that supports the view that they already have. And in fact, it's very difficult to even have a rational conversation about AI coding at the moment, I feel. Some research shows that developers feel much more productive, but in fact are slower. Some research shows that developers are producing more code, but it's of lower quality, which essentially means it needs more work, right? And we've seen the cost of bugs when they come back to developers later on in the pipeline. Some research shows that developers feel 10 times more productive, but actually only 10% more productive. There's just too much variation in this research right now. But here's the thing. AI is exciting. I think it's exciting. Exciting is both a positive and negative word. I'm excited by AI. I'm also a little bit distressed by AI, and a little bit worried about AI. I have emotional feelings about AI. And I don't know whether we're calling it AI development or LLM development or agentic development. I have a problem with that last phrase. Like, the word agentic makes me want to rip off my own ears. I don't know whether that's just me. And I was originally worried that agentic tools like Claude Code and Codex and Cursor would make me a code reviewer, like, full time. I don't think anybody loves code review. And to some degree, it kind of does make you a code reviewer all the time. It's part of the development cycle. You write specifications, you review the code. It's not as bad as I thought it was going to be. It's more creative than I thought it would be. I don't have to fight with a developer to get them to do what I want. I just ask Claude to fix whatever it did, to make it more like what I would have written if I was writing the code by hand. But I don't know about you. I've fallen into some bad practices. Like, I can feel myself falling into bad practices. I don't always read my tests. I find myself skimming the produced code. I don't spend a lot of time thinking about the architecture of my code, other than just making sure it's sticking functions in like the right file. And I feel like I've started to delegate my thinking to the machine, and that's not good. So everything I've talked about so far in this talk becomes more important with AI, not less important, and I'll go through some of that. Generally, working with large code bases confuses LLMs. It results in duplicate code in the wrong places. It results in tests that don't test what they're supposed to. Like, LLMs do weird things with code bases. So the first thing that's very important to know is, can the AI use a debugger? And I only mention this because we're working on this at JetBrains at the moment. We're trying to expose functions of the debugger to agentic tools to just sort of see what they do. Is that more efficient? At the moment, they do print line debugging. So it's a terrible way to debug code and work out the behavior of your code. If we give the agents the ability to stop the program in the middle and have a little look around and maybe step forwards and look up the stack frames and things like that, is that useful to agents? I think that could be a pretty cool tool. So if we can get this to work, then for the 70% of you in this room who never use a debugger, like you may never need to learn. Maybe you just ask Claude to do it for you. But in the meantime, I would say that at the moment, there's a need to sometimes run through the program to find out what's going on. So maybe use your debugger for that. Design is guidance for the agent. So this is one of the reasons I was talking about design earlier, as well as making you faster at adding features and extensions to your code. It gives the agent an obvious place to put code, and then it's more likely to do it when it reads the code and finds a place that just seems right. Having classes that can be extended or implemented to add certain functionality is something that the agent will generally do, especially if you tell it to, right? You're in charge of the design. You get to tell the agent what to do. Good structure guides agents towards appropriate solutions, whereas bad structure allows AIs to create chaos faster. Which, if there's a single summary for an LLM, I think that's probably it. In 2024, duplicated code blocks in code bases rose 8-fold. So since the rise of agentic coding, or at least LLM coding, like suddenly people are duplicating code, or at least agents are duplicating code all over the place. That's according to a survey by GitClear last year. So if you're ending up with duplicated code, you're kind of violating don't repeat yourself, which has always been a guideline and not a rule, by the way. But if you're doing it 8 times, you're probably making mistakes. So this is very much leaving design on the table. Tests are also guardrails for agents, so tests become more important. And whether it's you writing the tests or allowing the agent to write the tests and making sure that they properly test what you need them to do, like not just testing a subset of values, but checking boundary conditions and checking full ranges of values that might be input or output. Without these kinds of tests, you're just vibe coding, and that's not software engineering. AI-generated PRs contain 1.7 times more issues than human-written code, according to CodeRabbit last year, based on a survey of 470 PRs. So you need to either write or review your tests, because the agents are writing buggier code than you would write. So just a quick run through some AI things and things that matter less and matter more around sort of that code quality and productivity. Things that matter less are boilerplate code. It doesn't matter if you have repeated code in your tests, because the agent will manage that for you, and it will refactor those repeated code blocks when you need them to. Mechanical code generation, like actually just having lots of code written, especially like lots of functions that follow similar patterns. Agents are great at that. And then refactoring. So I mentioned earlier, like PyCharm originally became famous because it had all these refactoring capabilities that allowed you to move around code, and it would handle imports and things like that. You can do it on a much more powerful level with agentic coding tools now. It's surprisingly good. You can do things like take all the functions in this module that use the database and move them into their own database module, and it will just handle it. It will handle the links between the rest of the code. It will handle the imports. Make sure you've got some tests to make sure it did actually do what you asked, though. The things that matter more are judgment, primarily. Excuse me, I've got some notes here. How should this thing be developed? Like, what would it look like if you developed it yourself? What are the trade-offs you need to make? Because your agent shouldn't be making that decision for you. What is important? What is less important? Judgment. Design decisions. So again, like agents aren't good at design. They lean towards the ball of mud to some degree. They will constantly refactor vast areas of your application if you let them, according to whatever thought that the agent has had in the latest iteration. You need to think, is the design satisfactory at the moment? Could it be improved to make extensibility better? Is the previous design still fit for purpose, or do you need to do some kind of redesign of this part of an application? And then finally, are you building the right thing? So again, back to product management, find out what your users need, find out what you want to build, what you need to build, and make sure you're only building that. I like to summarize these as typing and thinking. If agents only end up taking away the typing, I don't think I'll be unhappy about this new world, even though obviously I love my keyboards. The key thing here is don't leave your core skills on the table. If you're adapting to development with AI, remember your debugging skills, remember your testing discipline, remember thoughtful design, but mostly thinking. Remember to keep thinking while you're working on your projects. AI amplifies your practices, both good and bad. So try to make sure your practices are good. If you can take one thing away from this talk, like just pick one thing. It's like write tests for that module that you've always been afraid to touch. Refactor that file that everybody dreads, that's just brittle and needs to be both understood and more understandable. Learn to use your debugger. In general, learn to use all of your tools, whether your tool is a debugger, an IDE, a CI platform, or just the keyboard that's already on your desk. Your back and your brain will thank you. Thank you very much.